Ad Astra is our mantra. Ad Astra to the stars. Ad Astra. It's who.
Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about small but mighty space telescopes. They didn't get all the fame of the Hubble, but they sure delivered on the science. I'm delighted to have with us Dr. Bradford Baer, astronomer and engineer. In 1992, he got his bachelor's in astronomy from Williams College in Massachusetts. In 2000, he got his PhD in astrophysics from Caltech. From then until 2003, he worked at the McDonnell Observatory in Texas and then began work at the Naval Observatory here in Washington, D.C. In 2007, he branched off into the private sector, bringing astronomical spectroscopy down to Earth. Welcome back to this table.
Thanks, Kent. It's good to be here.
All right. Tell us about these. Well, first of all, why do we put telescopes in space? Yeah.
Two main reasons. Both of them related to that pesky, annoying atmosphere that we have here on Earth. Most people are familiar with the twinkling of the stars. Astronomers are rather unromantic. We hate that twinkle because it means that it blurs our view of astronomical objects. So by putting a telescope up in orbit, you can get a much sharper view of the surrounding universe. The atmosphere also absorbs a lot of really interesting wavelengths. Infrared light, X-rays and gamma rays get swallowed up by the atmosphere. So if you want to look at an object that puts out a lot of energy in gamma rays, for instance, you need to go into orbit. And a lot of people are familiar with Hubble's very sharp view, but may not realize that there are probably 100 other space telescopes that have flown or are still flying, which are dedicated to certain very specific science missions. So I thought we'd talk about three of them today.
All right.
Hipparcos, Beposax, and WISE. Hipparcos was a European mission that launched back in the mid-90s. And its mission, its science goal was to do astrometry, measuring the positions of stars very, very accurately.
Including their distance from Earth?
And that is one way to measure their distance.
That's the hard part.
That's the hard part. Measuring distance is a very, very challenging part of astronomy, unless something like another planet is close enough to bounce a radar pulse off of it. You have to take an indirect approach. And using parallax, the apparent shift of a star relative to more distant objects as our vantage point changes, as the Earth goes around the sun, is how we know how far away most of the nearby stars are. And then there's a whole distance ladder, as it's called, that's based on those nearby measurements to figure out how far away more distant objects are.
So the basic principle of Hipparcos is parallax.
Measuring how the position of a star shifts over the course of a year.
In comparison to its background, the very distant galaxies, let's say.
The backdrop.
Okay.
And they this is a technique, this parallax has been done from the ground for decades or even centuries, but by doing it from space, they were able to make much more accurate measurements because the star images were a lot sharper.
Now, I understand they were also able to, over a period of years, reconstruct the motion of these stars.
Exactly. In addition to the little sort of circular wobble of many of these stars, since we're in a big swirling galaxy and everybody's going around, not necessarily at the same speed, stars tend to drift in a very consistent fashion, and they're, at least from our standpoint, because they're going a little bit faster or a little bit slower than us. So as well as measuring distances, Hipparcos was able to identify a number of moving groups, clusters, not stars that are in the same part of the sky, not particularly close to each other, but we measured them all moving in exactly the same direction, and this wouldn't happen just by accident. We think that these are the remnants of smaller galaxies that got swallowed up by the Milky Way and absorbed into the into the spiral, but they still have that same trajectory. And so these are clues to how the galaxy grew in its very early centuries.
So I understand the result of Hipparcos is a star catalog, and it really contains basically the XYZ, the coordinate, but also the motion, the three components, including how fast it's moving away or towards.
Hipparcos by itself wasn't able to get that third component. That's something you can measure with spectroscopy, my favorite subject, by looking at the Doppler shift, how much the certain
shift.
spectral pattern gets red shifted or blue shifted. So Hipparcos wasn't able to do it all by itself, but it did the lion's share of figuring out not only where these things are, but where they're going, and essentially getting a much better census of how things move around in the Milky Way.
So now I understand there were two catalogs that actually came out. One was a very high precision catalog and one a somewhat lesser precision.
Right.
Tell me, how accurate were these higher precision catalog?
It's quite remarkable with a little bit of post-processing with the data. I shouldn't say a little bit. A lot of effort went into months, years. I mean, the mission, I think, officially ended in 1996, but people are still working on these catalogs to this day to take out all sorts of little contamination effects or glitches in the data. The basic fundamental accuracy of this catalog, measuring the position or the angle between two stars in this reference grid, we're able to get it down to the milli-arcsecond level, where milli meaning a thousandth, an arcsecond is a 60th of an arcminute, an arcminute is a 60th of a degree, and a degree is a pretty small angle to start with. So the angular accuracy was equivalent to the diameter of a quarter, 3 million miles away. Very, very small angle.
Very impressive.
It's extremely precise, and that's how they were able to detect the parallax effect much more accurately and to much greater distances than you could ever hope to do from the ground.
Now, one of the things I guess one learns as a child if you have an interest in astronomy is that you don't necessarily know how bright a star is. You know how much light is coming into your telescope, but you don't necessarily know whether that's a dim star that's close or a very bright star that's far away. Now, this catalog changes everything, doesn't it?
Exactly. Knowing how far away it is, you can tell whether, as you said, it's a dim star that's up close or a bright star that's far away, and that has played a big role in our understanding of how stars work, being able to trace their evolution and being able to look at stars of a certain color, say, and know whether it's a red giant or a red dwarf. So, Hipparcos has had impacts on so many different areas of astronomy, from stellar evolution to the formation history of the galaxy. I think at the last count, over 5,000 different published papers use Hipparcos data. So it rivals Hubble in its impact on our understanding of the universe, even though it didn't produce any pretty pictures.
One of the things that always had a certain fascination for me was how the stars would flow around the galaxy. And I guess there's the smaller catalog has 100,000 stars.
Something of that sort,
and
right?
The slightly less precise catalog is over 1 million stars.
Right, and that's still only a tiny fraction of the total number of stars we think there are in the galaxy, but it's a good representative sample of what's going on in our neighborhood of the Milky Way, and lets us extrapolate to the whole, to what's going on elsewhere.
So it's everything down to magnitude 11, minus 11?
I forget what the exact limit is. These are stars that are quite a bit fainter than what we'd be able to see with our eye, but the telescope itself was only about 11 inches in diameter, but had a very clever dual mirror setup so that it could essentially look two directions at the same time and make those relative angle measurements with the high degree of precision we were talking about before.
Yeah, very impressive.
Yeah.
That's a game changer.
Yes, very much so. Not glamorous, but a linchpin of our understanding of how big the universe is.
Yeah. All right. Tell us about Beppo Sax.
Beppo Sax, it sounds like a Pokemon character, doesn't it? It's,
I do know. It's a cartoon, right?
The cartoon character.
Okay.
It was a joint Italian-Dutch space agency mission, and it was an X-ray telescope. It could detect X-rays and some gamma rays, and it was launched with a couple of different science goals in mind, but it became quite famous because it cracked the case of gamma ray bursts. Gamma ray bursts, you have some background
Well,
in
the background I have is I come from a defense background.
Exactly.
We kind of wanted to know whether other countries might be cheating on the nuclear non-testing treaty. So we had some satellites that would look for gamma
the Vela
emissions.
constellation,
Right.
I think it's
Well, they did pick some up.
These flashes of gamma rays
Right,
that
yeah.
Originally I assumed they thought, oh my gosh, there are nuclear explosions going off everywhere.
Right.
But it turned out that these were far beyond the Earth, that there were these just like flash bulbs in a
Somewhere in the
football
sky.
stadium
Yeah,
going
yeah.
off, dozens daily, and we had no idea what could be causing such.
So the big question is, where are they and what's the cause?
Right,
Yeah.
and again, going back to what you were saying about star brightness being some ambiguity about how far away it was. Some astronomers thought they were bright enough, it must be some relatively small flash within our solar system, or maybe out in the Oort cloud, maybe they were in the galaxy, although that probably wasn't the case because they were not constrained to the plane of the galaxy. We saw them in every direction in the sky.
Yeah,
But if they were in the far distant universe, they must be phenomenally bright in order to be seen from Earth.
Yeah.
So Beppo Sax was the first orbital telescope that was able to figure out when a flash went off, not just that it had gone off, but pretty accurately where it was in the sky. And it radioed this data back to Earth very quickly, and it was sent out through I think the internet was fairly new at that point. So these little automated emails would go out to observatories on the ground saying, we got a gamma ray burst at these approximate coordinates. Swing your telescope around real quick and see if you can see anything going on.
Now, it does have to be quick because these bursts fade
in a matter of minutes or
yeah.
hours for the longer ones.
Yeah.
And so only after Beppo Sax was in place were they able to catch some of these so-called afterglows. Most of the initial flash was in gamma rays, but then there would be an
afterglow in the X-ray.
Right, in the X-ray and even in the visible. And it was, I believe, in 1996 when the first really bright gamma ray burst was captured by Beppo Sax. A large telescope on Earth picked it up, saw a glow in the optical, and was able to get a spectrum of it, and found that it had a significant redshift, that it was nowhere nearby. It was a good fraction of the way across the universe. And that, of course, got all the theorists quite fired up about how can you create such intensity of radiation. I believe they calculated that the amount of energy release was equivalent to half of the sun's mass being converted into energy, which is a lot of energy.
It's phenomenal.
And subsequently, more research, and a lot more detections by Beppo Sax, and then other satellites following afterwards to do the same sort of thing. We've figured out that gamma ray bursts are probably, at least one type of gamma ray burst, is the collapse of a huge star, a supernova,
stars.
or even a hypernova, as they called it. And that when we see a gamma ray burst, we're getting lucky that the burst, because of the collapse, a lot of the energy squirts out the poles. And if
That'd be a rotating star.
a spinning star, and then a lot of the energy is released through the North Pole and the South Pole of the
like
star.
a searchlight. Yeah.
And so it's essentially a searchlight, and if we are lucky and happen to be in the beam of that searchlight, then we see the gamma ray burst.
I see.
So it's a focused energy rather than being distributed equally in all directions.
And so far, none of them have come from the Milky Way.
Right, and we really hope they don't. If a gamma ray burst goes off
that's
and
right.
it's pointed at Earth, we are pretty much toast.
Yes, yes. irradiate one half of the planet.
But no one should lose any sleep about that. It's extremely unlikely that that's
Yeah.
going to happen anytime soon.
Far too rare.
Right.
Yeah.
So BepOSAX only operated, I believe, for a couple of years, but it, as I said, really helped figure out, got the ball rolling as to what these mysterious flashes in the distant sky were.
Yeah.
And it's been succeeded by SWIFT, is one such satellite,
there've been
and
a
several
few,
others
yes.
to carry on the work. But
And I think they're more sensitive now, and I think we're detecting maybe one a day,
something like that.
where before it was maybe 2 or 3 a year.
right.
Yeah.
They've really upped the game, and as we detect more and more of these, we're realizing, there are a couple of different flavors, maybe due to different mechanisms. There's a certain type of gamma ray burst that may be due to two black holes orbiting around each other and finally merging.
Or maybe 2 neutron stars.
Two
I think it
neutron
was.
stars.
Yes.
That is a completely different sort of energy release mechanism, but it ends up looking somewhat similar.
I think that mode gives very short bursts.
Right. There are the short bursts and the long bursts.
Like a fraction of a second,
Right.
something like that.
The more we thought we had them figured out, and then the more we learned, the more we realized.
More complicated
wait,
it looks.
Mother Nature always manages to surprise us with something new.
Uh-huh. Well, tell me about WISE.
WISE, one of my favorite little telescopes, partly because I know some of the people involved.
Okay.
It stands for Wide Area Infrared Survey Explorer. It's a slightly larger, 16-inch diameter telescope, but like a fisheye lens on your SLR camera, smaller lens means you have a larger field of view. You can see more of the sky at once. And WISE's mission was look at the entire sky and do so in the infrared heat radiation.
Right.
Which
when you open your oven door, you feel
you feel that
Yes.
cooking off. So a lot of objects out in the universe put out a lot more of that warmth than visible light, especially those that are hidden behind dust. Stars that are just forming and haven't thrown off their cocoon yet.
So the dust would absorb the visible light, but it would let through the longer wavelengths.
Let through and even re-radiate. It would, anything that is above absolute zero will glow in the infrared, and that's what WISE is looking for.
Okay.
Both to do direct studies and also to essentially make a map of the infrared sky, so that larger telescopes like the Webb Space Telescope, Hubble's successor, which is going to launch someday. The launch date keeps getting pushed back, but
Yes.
they've constructed the mirrors. This is going to be bigger than Hubble and tuned to work in the infrared, but it's essentially a super telephoto lens. You want to know where to point it, and
Right.
what WISE's catalog is intended for, among other things, is to be able to select interesting things to look at with the telephoto telescopes.
Right.
But WISE has also been doing some very interesting stuff just by itself. There are this class of objects called brown dwarfs.
Yes.
They're so I like to describe them as being halfway between a planet and a star.
Right.
They do glow with their own light, but not from helium fusion, sustained helium fusion in their cores, just from the residual heat from their gravitational collapse. So they're failed stars after a fashion. They just weren't big enough to
ignite. Yeah.
But there seem to be quite a lot of them out there, and they're an interesting kind of missing link between stars and planets. And WISE, being sensitive to the dull infrared glow that these brown dwarfs put out, has discovered quite a few of them, especially much cooler ones than we've ever been able to see before.
I understand actually a whole new class of star,
Right.
which is really more like room temperature.
Yeah, the coolest one so far is just about what we would consider a comfortable room temperature, which on stellar standards is incredibly
amazing.
cold.
Yeah.
So these Y dwarfs, as they're called, WISE is also turned out to, as planned, this was no surprise, turned out to be very good at spotting asteroids in our own solar system, which asteroids and the material they're made out of are extremely dark. They only reflect a few percent of the sunlight that hits them.
It's dirty snowball, right?
Comets and asteroids, the dirty snowballs and the sort of floating rock piles or gravel piles.
Yeah.
So they're relatively small. Even the big ones are only 10 miles in diameter, which is a lot smaller than any of the bona fide planets.
Yeah.
So we worry that there are a lot of these rock balls floating around in the solar system that we won't see until they come streaking in through our atmosphere.
Ah, yes.
But they are relatively warm because they've been absorbing all that solar radiation, and so they show up much better in the infrared. And so part of the WISE mission was to look for infrared sources that changed position from
I guess we call them near-Earth objects.
especially the near-Earth ones, those that are in orbits that cross ours, which would pose an impact risk potentially. So WISE was in operation for a couple of years. The coolant that helps the infrared detectors work efficiently ran out as expected, and it was put into hibernation. But just a month or two ago, NASA announced that they would be waking WISE back up and using the two shorter wavelength infrared cameras that were still fully operational to continue the asteroid survey. And so the people working on that, I'm sure, were quite excited, and will be over the next couple of years getting a much more accurate census of just how many of these potentially hazardous rocks are floating around out there.
So it's, I know NASA has had a survey going on for a long time, try to identify all the near-Earth objects, at least above a certain size.
Right, exactly. Congress had mandated that they try to find 90% of those larger than some threshold diameter, and they believe they had done that, both using WISE and a lot of ground-based telescopes, and very complementary. It's not that the space telescopes render the ground-based telescopes obsolete. They can work together much more effectively. But I think there are also some very specific asteroid hunting mission plans being put together to follow up WISE with something with a larger field of view or a larger aperture to be able to see more distant or smaller, fainter asteroids.
Right. I'd like to go back to something you mentioned a little earlier, is that WISE would be used to look for interesting objects which could then be looked at with greater resolution by the Webb, if that ever gets deployed.
Right.
What kind of objects have we found, and what's curious about them?
Quite a few different sorts, and depending on which astronomer you ask, they might have a different answer. The galaxies very, very far away that we're seeing as they were just after their formation, only 1 or 2 billion years after the Big Bang, those galaxies filled with very bright young blue stars put out a lot of light in the ultraviolet.
Yeah.
But because they're so distant, because that light has gotten stretched out by the expansion of the universe, the redshift, due to the expansion of the universe as a whole, a lot of that ultraviolet light now shows up in the infrared. So one thing that WISE is looking for is the most distant galaxies. Also of interest are galaxies that are forming a lot of stars but are still shrouded in dust, and so they are glowing in the infrared. Ultraluminous infrared galaxies, ULIRGs. Astronomers love acronyms, and these ULIRGs are something that are very eagerly being researched. The brown dwarfs and such as well are going to get followed up.
Wondering about the population of the these brown dwarfs. In our neighborhood, about 80% of the stars are red dwarfs. We don't really have many of the yellow ones like our sun or like Alpha Centauri, I guess.
Right.
So the population of red dwarfs is pretty large. I'm wondering if the population of brown dwarfs may be even larger.
Maybe
is that
so.
Possible?
It's possible, and that's something that a lot of people would really like to know, because it tells us something about it. As these balls of gas collapse out of a larger gas cloud, how do they fragment? Do they turn into many smaller globules that then would collapse into a brown dwarf, or is there some sort of effect which makes them stick together or has a lower limit? So getting a good census of the brown dwarf population is going to teach us a lot about how stars of all sizes are formed.
Now I understand, I guess it's Kepler, right, has been looking for
exoplanets.
For exoplanets.
Right. This is another very and actually fairly famous small telescope because it's doing something quite exciting, finding perhaps the other Earths around other stars.
So I'm wondering if WISE could contribute in that area, because these planets don't actually give off their own light, but they're warmed by the proximity.
Possibly. Some of the larger space telescopes, like Spitzer, which is a medium-sized infrared telescope, has been used to look for the direct infrared signature of planets. And I believe that the Webb telescope is going to be used for that, as well as looking at much more distant things.
Be very impressive.
WISE, I think,
probably doesn't have the resolution.
Doesn't have the resolution, doesn't quite have the sensitivity just because it's so small.
Yeah.
It's not what it was designed for.
Sure.
I'm sure some clever graduate student might dig through the WISE archive, and it's once the map was completed and calibrated, it was released to the public, or at least to anyone who wanted to log in and pick out a little postage stamp of some part of the sky to study. So some planetary discovery very well may come out of it. We'll just have to wait and see.
All right. Well, thank you very much.
My pleasure.
That was Dr. Bradford Baer, astronomer and engineer. Thanks for joining us, and see you next time.